Good morning, friends. We are going to see the next part in the bonding in organometallic chemistry. And last time we have considered some factors and made some comments on the nature of bonding between metal and carbon in organometallic compounds. So we will see which are the factors to which the comments which we have made earlier are useful, and here we find that. So we will show this. So we will see the factors which will expect will be expected to lead to relatively stable metal carbon bond. So if we make the reasonable assumption that the population of antibonding molecular orbitals leads to bond breaking, assumption, if we make this assumption that the population of antibonding molecular orbitals leads to bond breaking. So this is our assumption. So any factor that increases this energy gap, between highest energy orbitals, means unoccupied, or highest, if we see the highest field orbitals, that is molecular orbitals, and the unoccupied lowest energy orbitals, that is bonding MOs and antibonding MOs. So this gap is important, and it is concerned with the stability of metal carbon bond. So the energy gap is important. So that is LUMO, and this is say HOMO, highest occupied bonding molecular orbitals. So this energy gap, we can say delta E, is of our greater concern. When this is large, the molecule, this metal carbon bond, is stable, and when this is small, this metal carbon bond is unstable or weak, we can say. So in such case, the molecule will undergo easily substitution reactions, and whereas when the metal carbon bond is stronger enough because of the large delta E then the molecule is stable. Metal carbon bond is stronger, and in such case the reactions are not easily possible. So in some reactions, even after supplying the necessary amount of energy of activation, this energy gap cannot be overcome, and in such case the supply of energy, that is energy of activation, also becomes unsatisfactory to complete the reaction. If we consider the D0 configuration metals, D0 metal ions in metal carbon bond, there is no electron in relatively high energy non-bonding orbitals. Means there is no electron in non-bonding high energy orbitals. That is, so these are T2G orbitals, that is non-bonding, and the bonding molecular orbitals are EG orbitals, and EG star means EG antibonding molecular orbitals are still higher energy than T2G orbitals. So in such case, the non-bonding molecular orbitals are accommodating the required number of d orbitals. So if these electrons are, so in this case the D0 orbital means there is no electron. When we consider D1 configuration, there is one electron. So in this way, in case of D2 there are 2 electrons. So in this way we can have variety of electrons. The distribution of electrons in these orbitals, that is EG and T2G, so that is EG and T2G, depends upon this energy gap. When the energy gap is larger, most of the electrons, maximum number of electrons, are accommodated in this low energy, that is highest occupied molecular orbitals, that is EG orbitals, and after remaining, means after completing these orbitals, the remaining electrons are going into the higher energy T2G orbitals. These are relatively higher, and the energy gap depends upon their conditions, with other conditions also. So if we see here the distribution of electrons of these cases, if we consider the D4 case, there is possibility, means the distribution of electrons depends upon, so these are T2G orbitals and these are EG orbitals. So in case of this D4 configuration, if all the 4 orbitals are entering into, so when they will enter into these orbitals, when the energy gap is large, when this delta E is large. So this configuration is possible when delta E is large, and we can have the configuration when delta E is small. So we can have these electrons like this and 2 electrons in this case. So when delta is small, the remaining 2 electrons, after occupying the lower energy EG orbitals, they can enter into these T2G orbitals because the energy gap is small. So distribution of electrons depends upon the energy distance, that is delta E. So in case of 4 to 6 electrons, the energy distribution, electron distribution will be in these 2 ways, depending upon whether the delta is larger or smaller. But in case of higher energy gap, that is D7 to D9, the delta E is large. Delta E is large. So all factors which decrease kinetic conditions, we will see all factors. Second point, all factors decreasing kinetic conditions. Kinetic conditions. So first of this is that steric hindrance. Steric hindrance. When the coordination number is higher in case of metal, then there is enough space around the metal ion, so that can accommodate the more number of and larger size ligands. So in that case, when the ligands of larger size are coming closer, then there is hindrance, means there is interaction between the ligands of larger size, and this will increase the energy. The larger steric hindrance will react with each other, and it will increase the energy of that bond, or we can say energy of the molecule. And in such case, the reactivity will go on, means metal carbon bond will be weaker. Then the inert configuration, like when we consider, say this is T2G and this is EG, then in this case this is inert gas configuration, means inert configuration means when there is complete pairing, means all electrons are paired like that in D6 configuration. If we see, then the distribution will show that the molecule is stable, means bond is also stable, and it will require more energy of activation. Second is absence of low energy pathways. Absence of low energy pathways. Like that in beta elimination. That is beta elimination. The factors which directly increase the metal carbon bond strength. Factors that increase the metal carbon bond strength. So these factors include the pi contributions to metal carbon bond. Pi contributions to metal carbon bond. So this contribution will strengthen, and this will increase the bond strength. This will increase the bond strength. So if we consider the ligands, when the ligands are pi type, means they will produce the bonding, means they will have pi electrons available for bond formation. Then in such case, so here when the pi contributions are available from the ligands, then if we take such general example of the complex ligand with pi contribution, then the reaction can be generally represented as metal plus MCO gives metal carbonyls. CON, and through kinetic effect. So this is one factor, that is thermodynamic effect. Thermodynamic effect shows that when the reaction is favorable in forward direction, the reaction will show decrease in the free energy. Decrease in free energy will direct the reaction in forward direction. Then second effect here is kinetic effect, that is, you can say we are in kinetic effect. So this kinetic effect increases the energy of activation input for the metal carbon bond, which favors the cleavage of metal carbon bond in organometallic compounds, because of which the alkyl group is separated from the metal, and as a result it can show the various combinations like this. For example, when we are having such bond, metal carbon bond, so after the use of energy of activation, the cleavage is favorable. So it shows that the two metal free radicals which are obtained will undergo the reaction like this, and it will give higher alkanes plus the metal. So these are the products of cleavage. The following table, we can use the following table. See this table so that you will understand the various factors. For example, CH34 titanium, here the metal has coordination number 4, and when we take this coordination number 5, we can have the another example like this. Here we say general M, and here M is Nb, niobium and tantalum. Then coordination number 6, we have examples like tungsten, and other example like Rm, CO5.